in this problem, we first start off with a list that just included the number 1, and we can do two things on this list. We can either increase any element in this list by 1, or we can take any element in this list and put it at the very back. And what we care about at the very end is the sum of this list. And we're given some number n, and we want to find the minimum number of moves such that we obtain a sum that is at least n. So if n is 1, the initial array has a sum of 1. So we don't do any moves on it, so we output 0. If n is 5, it would be 3. Why is that? So actually I just solved this problem, but due to an audio issue, things got cut out. So what you would do is, one way you could do it is you can increase this 1 all the way to a 3, and then you could put this 3 at the end again, so the sum is now 6, and now 6 is at least 5, so it would take us 3 moves, which is the answer. Now the key thing to notice is that it's always optimal to first increase the initial 1 to a big number, and then use that big number over and over and over again at the very end, right? So now let's look at the case of 16. Right? If we increase our number all the way until 3 first, and then keep on adding the 3 at the very end, we'll get 1, 2, 3, then 3, 3, then 3, 3, 3, 3, and so on and so forth. So the sum will be 6, 9, 12, 15, 18. And it takes us 7 moves to get a number that's at least 16 if we build the initial one all the way until a 3. If we build the first one all the way onto a 4, and then keep on adding that 4 till the very end, that'll only take us 6 moves. And then if you build it to a 5 and then try and get a number that's at least 16, that'll also take us 7 moves. So overall, we see that the optimal way is to first build the initial 1 to a 4 and then keep on adding that 4 till the very end, and that takes us only 6 moves. And the key thing to notice here is that 4 is square root of 16. So the answer to this problem is linked to square root n. And it turns out that square root n is the upper bound of the number that you have to build the initial 1 onto, right? So let's say we call this x, right? This here is x. To get to this number x, we need x minus 1 moves, right? So we 1, 2, 3, right? So this is this part. And then from this number, to get to a number that's at least as big as n, it would be the upper bound of n minus x over x, right? So in the case of this 4, to get x would be 4, and then n here is 16, right? So 4 minus 1 is 3, plus 16 minus 4, 12. 12 over 4 is, sorry, 12, yeah, 12 over 4 is 3, 3 plus 3 is 6, and so therefore this is right. So this equation matches with the number of moves, and we can test it with the rest, and then we see that we can find the number of moves using this equation in O of 1. So what we can do is we just iterate through all the numbers from 1 to square root of n, and then we just find the one that has the least number of moves, and we can do that in O of 1 time because of this formula. And so this is the code. So we just read in n, and then we preset answer to something that's bigger than square root n. So I just set it to a really big number, and then I go through all the numbers from 1 to square root of n, and you have to make sure that it's that it's inclusive. That's why there's a plus 1 here, because my for loop is less than, and then I just find the min of that, and then I make the function moves, in which it is basically this. So it's x minus 1 plus the upper bound, and the upper bound here is of n minus x over x is the same thing as n minus x plus x minus 1, because if you increase a number by x minus 1, but you divide that number by x, since C++ rounds down, that doesn't change the answer. So then this becomes n minus 1 over x. So yeah, this is how you find the number of moves in O of 1, and that's how you get the right answer as shown here. So voila.